Okay. Okay, so it's on, right? Yeah. Okay, so what we were talking about last time was sort of the, I think it's already on. It says power on. It's fine? Okay. So, it's getting in. So what we were talking about last time was kind of, let's say, the sort of like, in the last lecture, today's and maybe the next few ones are kind of the core of what we'll talk about somehow, in the sense of how thermality arises and that kind of thing. So what we did last time was we first made this observation that just by periodicity in the Euclidean direction, we can argue that there is a Rindler density matrix which shows up, which is a thermal density matrix. Okay. So what we want to do is we want to understand how, if you give me a density matrix, it would be nice to see if you can write down that as a reduced density matrix of some pure state. Okay, because then you can think of this as being part of some subsystem, in some sense. Okay, so this is partially what our goal was, and the way we started talking about it, where was it? Yeah. So what we saw was that by Weak-rotating this Rindler wedge, so Rindler wedge, when you Weak-rotate, you basically end up finding the polar flat space in polar coordinates, and then the periodicity of the angle direction basically tells you. Oh, doesn't move. This is the kind of stuff that we have to deal with, So yeah, so this phi. So I'm kind of forgetting where I left off. Can you remind me where I was last time when we stopped? So I think we were about to. So I wrote down the path integral and the ground state as a path integral, if I remember. Yes. Okay, so what we wrote down, so let me just recap that part anyway, because I think there was, maybe I went through that. It's worth seeing it twice, I think. So we had this Euclidean picture where this was, let me call it phi 2, and this was phi 1. So two configurations. This was my time direction, and this was my x direction. Okay. So the idea was that I'm putting two field configurations. I'm thinking of my path integral. So I started off with two path integrals like this. So let me call this. Okay, and so this is one path integral. This is one path integral. But then I imagine that I'm saying that these two configurations up to x equal to 0, I'm setting both of them equal to each other, and then I'm integrating over this phi tilde. Okay, so this is what I was writing yesterday. So this configuration is what we might call, I'll write an expression and then I'll ask you whether you understand it. So if we understand it, then I think we have not forgotten everything. Okay, so this is my, so this picture, so this line here basically means that I'm sort of imagining that this is where the cut is. This is phi 2, this is phi 1, and this is my phi tilde. And the idea is that I think of this path integral as the Euclidean time evolution in this direction to get me a ket, and similarly another one here. And then I imagine that the two joined here and integrated over here is given by this configuration. Okay? So the point is that now what I'm going to do is I'm going to reinterpret that same path integral. So this is now the picture. Okay? Once I have this, so I got this up to this stage, and doing this I got by starting from a Euclidean path integral where I'm time evolving in this direction or this direction. Okay? That's how I got these things. And then the claim is that, but sewing this part together, that basically now I have another interpretation for the same path integral in a different Hamiltonian language. Okay, so this is basically the trick. Maybe I think I mentioned it once, but it bears repeating, which is that if you start with, you write down your, an expectation value or some kind of Hamiltonian object, like a density matrix with some matrix element of a density matrix or a expectation value, any of these things, you think of them, you first write them down in some some path integral language. But once you get that object, you have another interpretation because the system has other symmetries. You can write it in terms of another Hamiltonian description. Okay, so that's what we are constantly doing. So here, for instance, what we did is that we used standard Minkowski time evolution, and we interpreted, that was the original Hamiltonian interpretation of this construction. Okay, so we have a particular Hamiltonian interpretation. Then based on that, we wrote down a picture or what kind of path integral this is. This is what this means. Okay, so that's what this guy is. And then we reinterpret that in terms of this new Hamiltonian evolution, which is basically the boost generator in Lorentzian signature, or here you can think of it as a rotation in polar coordinates. Okay, so this is the picture. And by doing this, we computed the density matrix of Rindler, and I think we wrote down that as e to the minus 2 pi times h Rindler. So this was what we did in sort of the first part of our calculation. Okay, so essentially the point will be that, so if this you can think of as this result that I have here would be this guy within phi 2 and phi 1. Okay, so the matrix element of that between phi 2 and phi 1 is what this path integral computes. That's the claim. And by doing it, we have also learned that the thermal periodicity is 1 by this guy, 2 pi. So that also comes out completely trivially. So it's that's the power of path integrals. We have not done anything calculationally, but we are getting we are getting actual quantitative answers. We found that the temperature is 1 by 2 pi, or the beta is 1 by 2 pi by doing this. Okay, so it almost looks like we did nothing, but the real thing that has happened is that we are using symmetries very powerfully and switching between different Hamiltonian descriptions of the same path integral. That's what we are really doing. Okay, and that means that the Hamiltonian has to have multiple symmetries or multiple time. In Euclidean signature, it has two different time evolution descriptions. That's essentially what we are exploiting. Okay, so the thing that I think the place where I sort of stopped, or at least a place where I can start from today, is this ket that I wrote down, which we have written that down many times, which is that tau equal to 0, and you have some phi sitting here, some field configuration, and the time evolution is this way, and this is whatever, anything. The pass boundary condition doesn't matter. So this is the same thing as where this is phi is arbitrary, and this is phi is let's say phi. Okay, so this is this path integral is essentially wave functional for the vacuum. Okay, I'm writing down the wave functional for the vacuum, and this is my wave functional. And now this is where I mentioned the most crucial fact here, which is that this ket, a general ket phi, can always be, I already mentioned it here, but it's sort of, for instance, if you have seen the derivation of Unruh effect, for instance, in more conventional, Bogoliubov transformation type of description, this may not often be emphasized. But because in Bogoliubov transformations, it essentially means that it's a change of basis. Okay, so if you have a basis in Hilbert space and you change the basis, you will often find that, as a result of it, you end up finding some kind of a temperature. We'll do that as well at some point. But here I want to emphasize that one of the things that is often, I think, underemphasized there is that there is a factorization of the Hilbert space that happens here, which is that this bra is basically phi L, phi R, where I think of this t equal to 0 line as this is phi L and this is phi R. Okay, so this is t equal to 0. And sorry, this is this is t equal to 0, this is the x-axis, this is t if you like. Okay, so and this factorization is something that we make an assumption about. Okay, and as I said, in standard quantum field theory, there is even though intuitively and for various calculational purposes we can use that to be true, but it's not technically quite right. Okay, factorization of the Hilbert space is not really a property of quantum field theory, but nonetheless, it gives the right answers. Okay, so this is related to, so you can always think of quantum field theory as an Ising model with various spins on a line, if you like. So for various purposes. So, and now what the claim is that this ket, so now what I want to do is I actually want to write down, I want to see, so what I want to do is I want to see this density matrix which I computed here. I want to see the origin of this density matrix as a reduced density matrix in some pure state. Okay, so what so for, you know, because of the malice of hindsight, so to speak, I'm starting with my Minkowski vacuum as my pure state. Okay, so I start with, you know, this ket here. So when I specify some field configurations here, and I'm just going to look at some vacuum state. Okay, so the Minkowski vacuum state. So that means that, so I can use this guy. So now I consider this object. I mean, okay, let me call it omega, or I might switch between omega and 0, but it's always the vacuum state. Okay, there's no real difference. So this, now I write it like this. And so the same sort of thing that I did here, which is that here I wrote down a path integral, wrote down an expectation value, and now I'm going to write this same expectation value in a different Hamiltonian description. And the Hamiltonian is what I told you last time, was the half boost on the right, or you know, in the Rindler half. So Rindler means half of this, this half line is sometimes called the Rindler half line. So, so the point, again, I'll emphasize because it's been a few days, all of these all live in different Hilbert spaces. Different Hilbert spaces. So this is in the Minkowski Hilbert space, this is in the right Hilbert space, and this is in the left Hilbert space. So these are the three guys that we have. And the claim is that this guy is also equal to Rindler times. Okay, so this is what I wrote last time. So this is the expression, and what we want to do is, so this is you can kind of see why this is the case. So what I had last time was I had a phi L here and a phi R here, and this expression basically means that I view this expression as a path integral this way, but now I'm going to view this as a path integral in this direction. Okay, so that's essentially what I'm doing. So by that logic, this guy is sort of the initial state, this is the final state, and I'm just writing it in this way, and I'll explain what the tilde means, and this pi is obvious because the rotation is by an angle pi, and this H Rindler is basically just the rotation generator in Euclidean signature. Okay? So the only thing I really have to explain is this. In fact, I have to also explain a little bit about this. So I'll start with this because it's a little bit easier. Okay, so this H Rindler is the same operator that I wrote last time, which is the boost operator. Because if you remember, the boost operator is the generator of time translations on the right Rindler wedge. Okay, so I'm going to reinterpret the same expectation value as an expectation value in a Rindler Hilbert space. Here it was a expectation value in a Minkowski Hilbert space. Because these are all complex numbers, so I can reinterpret in terms of some other Hilbert space. It's up to me if I can do it. Okay, so here I am interpreting that in terms of time evolution of a certain kind in a Rindler Hilbert space. And so why this? So all of this I'm interpreting in the right Rindler half, and that's why all these subscripts are there. I'll explain what this phi tilde L is in a second. Okay, so this H Rindler I said is, sometimes it's also called K right, which is the Hamiltonian, the boost in the right half. And the reason why it's important is because I wrote down an integral. I'm not going to repeat it again, but you might have it in your notes, or you can look at the videos. Is some integral, the boost charge is an integral on the real line. So the boost charge is an object associated with Minkowski-Hilbert space. Okay? Because Minkowski theories have, the 10 Poincare symmetries that we mentioned. So among those 10 Poincare symmetries, Kx is what is called the boost. So, but the difference here is that when I wrote the boost as a symmetry, I basically have to write it as an integral from minus infinity to infinity in dx. Of course, it has other dimensions as well. Let's say dy or whatever dy. It's a Hamiltonian integral, so there is no dt. It's on a time slice, but it might have y, z, whatever. But the specific thing about the Minkowski, I'm just emphasizing the fact that the integral is actually from minus infinity to infinity. Okay, in a proper, if it is a boost in the x direction, it will be some integral of this kind. I don't care what is inside, you can look it up. Okay, so, but the point is that this guy is only well defined as an operator in the Minkowski-Hilbert space. But what I care about here is only in the x greater than 0 part. So this integral, when I say that my kr, which is the boost generator that translates in the Rindler time, that guy is integrated only from the same integral but from here to here. Okay?
Just elaborate this integral from take the phi of r get the phi at the power 10.
So this guy, sorry. So this is, how did this happen? I'm going to explain this in glorious detail in a minute. So here I'm just kind of intuitively just saying that this object, this phi L phi r, this is what I basically wrote as ket phi in Minkowski-Hilbert space. That guy is, I wrote this down here. Basically this is the Minkowski path integral. Okay, I'm just integrating in the lower half plane and finding some configuration on the real line at t equal to 0. Okay, but I'm saying that same configuration, I can interpret that as split between phi L and phi r. I kind of distinguish the left half and the right half. I'm splitting my Hilbert space, splitting my spatial slice. Oh, x greater than 0 and x less than 0. Okay, and then I'm saying that my phi L I can view as an evolution in polar coordinates, if you like. This is again, note that all these, whenever I'm doing these integrals, they're all in Euclidean signature. So this was a Euclidean signature path integral. So similarly, so that means that if I want to go from here to here, I basically have a polar rotation available to me. So that's one of the symmetries of my system. So that rotation I use, and the generator of that rotation is basically Rindler, this H Rindler. Okay, but the point is that when I'm talking about it in terms of Lorentzian signature, this boost, because my metric, if you remember, so this is my Minkowski signature or the Lorentzian signature Rindler wedge, and the same thing went into this when I did my Euclideanizing. Okay, so this rotation in Lorentzian signature is a boost generator. This is we also did that in the context of this Rindler, accelerating particles and so on. So this guy is moving in this direction, and so that means that this generator here is basically the rotation generator in the Euclidean signature, or equivalently boost generator in the Lorentzian signature. But the boost generator in the right Rindler wedge. Okay, so the right Rindler wedge stands here, is this. Okay, so this is my eta, if you like, and the generators are just moving between, from one value of eta naught to another value of eta. Okay, that's what it's doing. And the point is that because it is only on the right Rindler wedge, I am only considering the integral only on the right half line. Okay, so there are various small things here, and all of them are somewhat treacherous. So if you are not clear, just ask me. I'll try to repeat. So the point here is that there is a boost charge in Minkowski space, which we are all familiar with, or at least should be familiar with, because it's part of Poincare algebra. So, and the key point about that, it integrates over the entire spatial slice. Okay, so that's the boost charge. But the point is that that same boost charge, when interpreted as a generator on the right Rindler wedge, only needs the integral on the right half line. Okay, and you can in fact check it more directly, and this is, if you like, it's an exercise, which is that you can write down. Yeah, let me finish this one thing, and then I'll take your question. So you can write down the scalar field on the right Rindler wedge, right? So this is, so I can, the general action is of this form. Let me call it d for x, d mu phi, d mu phi. I'm explicitly making the metric kind of here. Okay, so this is my scalar field action, and you can plug in this g mu nu to be this guy. I mean, let me make it two-dimensional to make it easier. So just rho and eta. So if that is the case, note that that x stands for this eta and rho. You can compute the Hamiltonian in that language, and if you translate to Minkowski coordinates, which you know how to from rho eta to xt, you will find that it has the form of the half boost integral on the right half line. Is that statement clear? If it is not clear, I can repeat. It's an important statement. So what I'm saying is that the Hamiltonian, so what we are saying is that the boost, half line boost in the, on this side is nothing but the generator of time translations. In other words, the Hamiltonian of this scalar field written in this language. So and naturally the integral will be only on the right half line. Okay? So that's an exercise. If you don't know how to compute the Hamiltonian of a theory like this, that's also an exercise. Can't go all the way back, but compute the Hamiltonian. Compute the Hamiltonian of this in Rindler coordinates, Lorentzian Rindler coordinates. And change coordinates back to Minkowski. To show that this is basically what we are calling H Rindler. Okay, compute the Hamiltonian H Rindler. Show that H Rindler is Kx, where x is only on x is always positive. Okay, so Kx is I mean this x just means boost in the x direction. It's not locating. It's not saying anything about the position of x or anything. And here the x means, I mean, in order to do this, I have to do an integral on spatial slice, and the x is limited to the positive half line. That's what this means. So all the x variables there are dummy variables. There is no real actual x anywhere. Yeah. That's right. Yeah. Because here it's part of the Hamiltonian, right? It is just, if you write down this thing, you will see that this spacetime has an eta going to eta plus constant symmetry. So that means that this action, because it doesn't contain an explicit eta anywhere, it respects that symmetry. So, and that means that there is an associated charge with it, and that charge is what we are calling the Hamiltonian. And that Hamiltonian, the claim is that it is just the same thing as the Minkowski boost Hamiltonian, but integrated only on the positive half line. Fine?
I mean, if I just think naively, I could have had some exchange between the two sides.
Yes. Mm-hmm.
And somehow you're saying because there are symmetries, it ensures that there's two sides interacting, you still have.
What do you mean two sides are interacting? See, these are all local theories, right? So this is a causal wedge. So all the data here completely fixes everything that happens on this right wedge. So there is only data. So if you evolve scalar field equations on this line, it will completely fix everything that happens on this. This is a causally independent region. So in order to fix evolution within this wedge, I will never need data from anywhere here.
But we did evolve only in Rindler coordinates.
Sorry?
We did evolve only in Rindler.
Yeah, the Hamiltonian is basically a Rindler Hamiltonian, right?
I went from t equal to 0, let's say, time in the future.
T equal to 0 means you're now talking about Minkowski.
Which is that time?
This one?
Yeah, the one there.
You can come here if you want. So this one? Yeah, so here, but it's only, I'm just talking about evolution along eta on the right side.
But in Minkowski, if I went a little up.
Yeah, but in order to evolve in Minkowski, I need the Minkowski Hamiltonian, right? I only have, here if I'm living with a theory which is defined only on the right wedge, which I'm allowed to do because this is a causally complete region, So that's what I mean by this. So this guy's integral, this d square x, is only on here.
It's a naive question.
Sorry, that's fine, yeah. Naive questions are the best. I can probably answer them.
A little in the future,
Uh-huh.
if I draw a straight line there,
You mean, so
I'll be missing this region in the center.
this line is what you mean?
In the center, I'm missing.
No, I mean, okay. So this, you're talking about this line first of all, correct? Yeah, okay.
The region in the
No, I miss everything to the left of this wedge, right? Not just the region in the center, I miss everything to the left of this.
my question was
Uh-huh.
at equal to 0, the sum of the two charges in the two wedges
Uh-huh.
is equal to the total Minkowski.
Boost, yeah. Mm-hmm.
If I go in the future, I'm missing this piece in between.
But depends on what you want to do with it, right? I'm just saying that this, the time evolution on this wedge I can accomplish by the boost charge integrated here. I'm not saying anything about what happens to anything else. So maybe you can ask the question one more time, because I think that some level of discomfort here is sort of natural, but
Yeah, just that region in the center is.
so we are not trying to evolve it there. Maybe I'll draw the picture one more time here. So let's see. So what do I need here? So I'll just delete this. Okay. So just draw that. So this is the thing, and let me not draw the other half. So this is my Rindler wedge, and you want to look at some line here. Okay. So that line is sitting there, yes, and
So I want to look at the full picture.
okay.
The sides and I have a Minkowski.
Yes, then you have to worry about more than what I have said so far. Because I'm just talking about the fact that boosts on the right half line are the Hamiltonian for evolution in Rindler time on the right wedge. This is the statement I'm making. It is, if you want to understand what happens, in the rest of, if you had a field theory specified here, what happens is a separate question. But note that the important point here is that H Rindler is a complete system. So you can evolve things completely over here using the Hamiltonian that I mentioned here. So it's a completely independent system, and how one connects it with the rest of the stuff is where a lot of the interesting things will happen. But at the moment, I'm just saying that you can start from here, and because if you the way in which we decide whether a quantum field theory can independently exist or a Hilbert space is complete, or evolution is within the Hilbert space, is by looking at the fact that essentially field theories are second order differential equations, right, in some sense. So that means that if you give me some data here, which is the field value and its derivative here, I can determine everything that happens here. Nothing else will affect it. It doesn't mean that I couldn't go here, etc. That's not the question, because we are quantizing the field theory. So I could have some data here and some data here which might affect something here, but I don't care, because that's not what determines the Hilbert space and the evolution within the Hilbert space. Okay? I can do various things. There are various other things that can happen. So if I specify data here, I will be able to determine things here. Okay? So so what we mean by evolution of a wave equation is basically the fact that if you give me this data, I can fix it at some later time. So this is what is called a globally hyperbolic region. So globally hyperbolic just means that hyperbolic differential equations, which are basically what wave equations are, they can be integrated consistently within that region. And that's all I need in order to make these statements at the moment. Okay? So yeah, sure.
So these are both infinite Hilbert spaces on the right and the left.
Right, yeah.
So does the half really mean?
Yeah, so that is a kind of a subtle question that I think somebody else asked this earlier. So this point here is in some sense a toy model for a firewall. Because the question of whether things are smooth there in the setting of various various questions that one might ask, that's related to the question of whether this point here is smooth in some sense. If it is smooth, you say that it is a firewall. So we are not really gotten there yet.
Even in Minkowski, I know it's smooth.
Right, yeah. It is in Minkowski, there will be a natural notion of smoothness there, as we will see.
So does the half mean infinite in Minkowski? Would I have done one for a minute?
It is the boundary which an accelerating observer will basically not be able to see, right? So this is it's basically the intersection of the future and past horizons for him. So if you like, in In Minkowski space, it is, it's fundamentally, this is just an arbitrary split, right? This is just an arbitrary split of one half and another half, so it's not very meaningful. But in the context of black holes, as another question was asked a long time ago, is at this point here it is basically really in some sense a point if you suppress the extra coordinates. But in the case of a black hole, this point is actually a sphere, and it's called the bifurcate killing horizon. It's a name, but it's good to know it because people will always use it. Okay, and the fact that that sphere has zero, its non-vanishing radius, is the reason why you can go into the other side of the black hole and various other things. Here, that's not really possible because it's manifestly just a trivial point in Minkowski space. It's just that whatever we are doing here has to be some sort of a coordinate artifact. Okay, so that's what we will. So yeah, I think that you can ask some of these questions are maybe also slightly premature. So I think that once we have all these things. And I will still not be able to answer this last question very well, I think. What really qualifies as the smoothness. But I think some of these questions that you're asking, I think they might just go away if once we see the end of it. Okay? Yeah, sure.
In the left-hand side,
yeah.
calculating in Minkowski.
Right.
The inner product.
Right.
You have an arbitrary choice of field radiation time, omega.
Yeah.
Or on the right side, you don't have any arbitrary.
Right, that's actually a good question. So essentially some sort of an assumption about the boundary conditions of the field in the far past in Euclidean time is implicitly assumed. Yeah, so it is true that here it looks like I didn't have to, So what it is really saying is that the field configuration that I specify in the far past doesn't matter. That's what it is really saying. Okay, so when we do this integral, it is less manifest in some sense because it is not, the boundary condition will have to be specified in terms of these field configurations which are, here on the other hand we are specifying it at some time slice here. But here what I'm really saying is that there is a boundary condition on this Euclidean manifold which is at somewhere far away in Euclidean past infinity or something, depending on how I define my time. That boundary condition doesn't affect my answer. Okay, and that's usually a valid assumption because we typically always assume that in space field configurations always die out at infinity. This is what our typical assumptions always are. So it is at least until something blows up and hits us in the face, we will believe that that's okay. Okay, so so this is the first thing. So the first thing I wanted to say was what is this Rindler Hamiltonian? So the claim is that the Rindler Hamiltonian is basically half of a boost charge in Minkowski space. Okay, and it's also important to remember that the boost in full Minkowski space, it rotates this line. Okay, it's not eta this way and eta this way, so there is a break here. That partially answers this question. So it is basically rotating the thing this way and not, yeah. So that's something to remember. All right, so. Okay, so now let me talk about the second ingredient, which is basically a form of time reversal. Okay, so I'll call this, so phi tilde L. So yeah, so this phi tilde L is tricky because I'm thinking of this phi L in this language as this. Okay, so and the point is that this thing, or equivalently this thing, they live on the right Rindler wedge, but this guy lives on the left Rindler wedge. And this is related to the fact that, I will explain what CPT is. CPT, how many of you have seen CPT invariance? Yeah, most of you. So CPT invariance is basically a symmetry of quantum field theory. Okay, some version of CPT invariance is always valid. Okay, so yeah, CPT has the way it is conventionally defined has various unnecessary complications. So to make things simple, I will, yeah, so let me define it this way. So in 2 dimensions, the operator that switches tau x to minus tau minus x in Euclidean field theory. Okay, so there is a So, and the key reason why this operator is interesting is because this is always a rotation. Okay, so let me draw a completely trivial picture so that it is very clear. So what I mean is, so let's say that you start with tau x, where tau and x are this way. So and then I act with CPT. CPT is basically some operation. And if I do that operation, what it basically does is tau goes to minus tau and x goes to minus x. So this means that this is my x now and this is my tau now. Okay, so the signs of the real lines are flipped. But the key observation is that now I can do a pi rotation. Clockwise rotation by pi, and then I again get back with, or maybe I should just do it, clockwise rotation by pi, and I get back with this. Okay, so that means that CPT can be thought of as a rotation of CPT in the sense of, here I'm talking about CPT. This is the reason why I said that CPT is a kind of a unnecessarily tricky thing to define, but really what it really is saying is that what is fundamentally important here is that in any number of space-time dimensions, if you flip one time coordinate and one spatial coordinate, that is always understandable as a rotation. Okay, so time reversal together with this parity operation. So the problem with CPT is that this is not typically called parity. Parity is basically the flipping of all coordinates. But then you have to distinguish between even number of dimensions and odd number of dimensions, and the conventional CPT that you see in 3+1 dimensional Minkowski space is not really true. That doesn't generalize immediately to higher dimensions. But if you phrase it in terms of one spatial dimension and one time dimension, this is true in any dimension. So this is, Witten distinguishes between this, he calls it CRT. Okay, CRT is, because R stands for reflection of X. Okay, so the point is that CRT is a symmetry of any Euclidean quantum field theory just by the fact that rotations are a symmetry of Euclidean quantum field theory. Any rotationally invariant. And Lorentz invariant theories, when you are in Euclidean signature, they're always rotationally invariant. So that means that any theory that is rotationally invariant in Euclidean signature must necessarily be invariant under CRT as well. But CRT, the crucial point about it is that it's a discrete symmetry. It's not a continuous symmetry. Okay? But nonetheless, this particular discrete symmetry is actually a symmetry of all Euclidean signature theories, if it was just a statement about Euclidean signature, this will also not even be interesting. But the point is that when you Wick rotate back to Lorentzian signature, this has interesting consequences. That's the reason why we care about it. Okay? So if it was just Euclidean signature and it stayed in Euclidean signature, we don't care. Because it is just, obviously, it's just a rotation and it's a rotation invariant theory, and we move on. But the point is that because of this fact that it mixes with analytic continuation to Lorentzian signature in interesting ways, that's why we care about it. So this symmetry in higher dimensions, therefore, not in higher dimensions, in a Euclidean signature, therefore often has interesting consequences in Lorentzian signature. And because we define Lorentzian theories by analytic continuation, we can, this is essentially sort of the poor man's proof of CPT invariance in Lorentz invariant theories, or CRT invariance in Lorentz invariant theories, because we define all our Lorentzian theories by analytic continuation. So if this is true, then something has to be hold in, go on.
In Euclidean space, we don't call it because it's a rotation.
It is also a discrete symmetry. See, you can also talk about t going to minus t and x going to minus x, right? So, you have to distinguish between symmetries of the space as well as symmetries that are realized in the theory. So a theory is something that lives on this space, and even if the space has, it might be Minkowski space, but I don't have to necessarily write down an action which respects all these symmetries. This is a choice that I have. But what I'm saying is that in this particular case, this particular discrete flip, this particular combination must necessarily be a symmetry if my theory is designed to be rotation invariant. Because this flipping, these two flips together is always a rotation. Okay? Yeah.
C part has to do with
No, it's again, that's one of the problems with the CPT, because it doesn't have anything to do with, it's a historical artifact in some ways. So what really one should be calling this is, for various historical reasons, this operation, this is really what T is. But on the other hand, this, for various reasons, it is called CT. And it has to do with the fact that, So time reversal is basically an anti-unitary operator. We'll say some of those things here. So and if it is an anti-unitary operator, it flips baryon and lepton number. And people in the beginning did not want to introduce a symmetry which flipped baryon and lepton number, or the charges of the particle. So then they had to by hand introduce a new C, as charge conjugation of baryon, lepton number, and so on. So, but this is really the Euclidean thing, time reversal invariance, that becomes the respected symmetry when you go to Lorentzian signature. Okay, so yeah, so I'm not going to say why this is called CT as opposed to PT. It's just a historical curiosity for our purposes. Okay.
CPT is independent of Poincare. CPT invariance, and Poincare invariance are independent.
What do you mean? See, CPT invariance is a statement about the Hilbert space of the field theory, right? CPT invariance is a statement about the Hilbert space of the field theory because it's saying that the theory has an invariance. So it's implemented in using some unitary or anti-unitary operators and so on, and then the expectation values remain, or the absolute squares of expectation values remain invariant under these operations. That's the real statement of CPT. So it is not just a statement about the geometric symmetry. So here, for instance, the statement is, so the point is that because of this geometric symmetry in Euclidean signature, field theories that you write down here, which are rotationally invariant, must necessarily be CPT invariant. That is the statement. Okay? So, and field theories, so the action, whatever you do with the field theory, it doesn't matter, whatever Hilbert space that you will have in the theory, because if you construct it to be rotationally invariant, it will necessarily also be CPT invariant, because of the fact that CPT is nothing but a rotation. That's the statement.
But this is not realized under Poincare, the rotation. This is
See,
transformation under Poincare.
so how this, that's a question about how analytic continuation works in CPT. So analytic continuation works, and also how it is realized in the Hilbert space, etc. So those are like, we will have some things to say about it. They are kind of like, that's a huge, there are various things one can say. So I'm just saying one minor thing here, which is that if you have, there are two things to distinguish. One is a geometric symmetry, and the realization of that symmetry, and let's construct a theory which respects that symmetry, then how that symmetry acts on the Hilbert space. Okay? So the claim is that because of this geometric symmetry, this CPT has to have, has to be a symmetry of the expectation values in the Hilbert space. That's the statement. Because of the fact that if you construct the theory to be rotation invariant in Euclidean space. Okay? So, right. So the operator that switches, so this is really what we are doing. But we will, generally speaking, call it CPT because in even dimension, CPT and CRT are the same. Okay? The reason is, there might be, you can always pick the tau and some coordinate direction, and there you can implement this. Okay? And the full flip of the rest of the coordinates, if there are even number, always, pairs of flips can always be written as rotations in any dimension. So, but the problem is that if you have an even or odd number of dimensions, then you might have like an, kind of a singleton dimension where you cannot do this pairwise rotation business. So that's why the odd dimensional cases are a little bit different, which is why it is more convenient to talk about CRT, which is basically just needs t and one extra x dimension. Okay. So, yeah, so this is, so the next observation, if you like, is that CPT, I'm just going to call CPT as like one operator, okay? So sometimes, it's, you should not really think of a CPT, etc. separate. You just think of CPT as the operator that implements your, this flip, if you like, okay? So we don't really care about the split between C, P, and T, and so on. So this is essentially the Lorentzian definition of CPT invariance. And this is just coming from, the reason why this is the way in which symmetries are realized is not entirely clear from what I have said so far, but you can look at Weinberg's second chapter if you like. Okay, all symmetries have to be realized in terms of unitary or anti-unitary operators in the Hilbert space, and there is a particular way in which they transform. This is a fundamental property of quantum field theory. So the only thing, you might have seen similar things where, if you have, let's say phi of x you dagger lambda is, you might have seen like phi of lambda inverse x, that kind of thing, where lambda is a Lorentz transformation, right? So this is the same sort of thing. The only real distinction here is that here you should think of this as an anti-unitary operator. So an anti-unitary operator is basically an operator which flips. This is what an anti-unitary operator is. Okay, we will say a few more things about it, but very crudely what that means is that you have to think of an operator that flips the sign of I. And time reversal is the only operator really that does that. And here it comes because this thing involves some form of time reversal inside it that eventually leads to some form of anti-unitary. Anytime you multiply a Hermitian unitary operator with an anti-unitary operator, the result is an anti-unitary operator. So that's the reason why this is happening. So, because we are working with a scalar field, which is a real scalar field, this phi dagger doesn't really matter. Okay, so and that means that because it's a real scalar field, this in some sense it's a little bit simpler. All it is really doing is that it is flipping the t and x, just like I said here. Okay, so that's what this operation is doing. And yeah, so let me just say a few words. I'm sure some of you may have seen it, but CPT is anti-unitary. So that the reason behind that is that your time reversal. So if let's say you have some operator that implements time reversal. So if you want to implement time reversal, basically this is what we want. We want to flip the sign of minus I. Right? This is your time evolution operator. So time evolution is reverse basically means there exists some operator, let me call this T inverse. Okay, such that this thing is e to the IHT. So that's what I mean. So this the e to the minus IHT doesn't matter. So you can think of this as, if you like. And so there are two options in front of us. One is that if T inverse is minus h. So if you demand, so I'll leave it as kind of an exercise here. T inverse is, if T inverse is minus h, you can show that under time reversal, the eigenvalues of eigenstates will flip sign. So which means that your Hilbert space is unbounded from below. So we want the ground states of theories to be stable. You don't want them to decay to something else. Okay, so that's what I call stable system. So if that is the case, you don't want this. So this is not okay, because if you do this, that's what will happen. So instead what we do is we declare that this guy takes you to this. This is what we say. And this is the definition, essentially, of an anti-linear, anti-unitary operator. Okay? So, yeah, I mean, there is a few things one has to say here, but we don't need most of it. So I'll just say one fact here, which is that CPT and time reversal also, CPT is an anti-linear, anti-unitary operator. Okay, so if you want, you can look at Weinberg. Weinberg has a clean discussion, volume 1, chapter 2. Okay, so 1 page, 1.5 page, and there is, if you want to really see how these things come about, you can look at his appendix also. He derives these things in elaborate detail, or you can just believe it, which is easier. You know what I'm saying? Okay. So yeah. So now what I'm going to do is, after this explanation. So what I said was that.
So the statement that you wrote, is this in Minkowski or
this here? This is in Minkowski. Minkowski means. Yeah, this is in Minkowski. You mean like, are you distinguishing between Minkowski versus Rindler? Yeah. So this is in Lorentzian signature. Yes. This is in Lorentzian signature.
Health is not a property of this geometry.
So yeah, it is not. It is not. Yeah. This is a property of quantum field theory. How symmetries are implemented in quantum field theory. So this is one of the things that Weinberg proves in the chapter 2, which is that anytime there is a symmetry in the system, the way in which it is implemented in the Hilbert space is either via a linear unitary operator or by an antilinear anti-unitary operator. And time reversal is one of the few for which that is true. And that's why I wrote, this structure is very similar in some sense to what you have seen for instance, Lorentz transformations or translations. The only real difference is that this is anti-unitary. So this operator you should not think of as a unitary operator. It's an anti-unitary operator. It's hard to keep in mind. All this because our psychology is so wired towards operators in Hilbert space being unitary. So you might, so even if I say it, I don't mean it. You know what I'm saying? Sometimes I might accidentally say unitary, but I mean anti-unitary. So, but the time reversal is also reversed, right? So, it's conserved in the, if you like, so, it's certainly conserved because the way in which you derive a statement like this is by demanding that the expectation value squares or probability squares, so this amplitude squares are preserved under these transformations. That's how you derive the statement about antilinear and anti-unitary. So, it's definitely preserved, yes. So, but I'm saying that it's essentially happening because the time reversal is making your evolution go backwards. That's what this anti-unitary, anti-linear business is doing. It's not so much about, it's not a strange thing in the forward direction. It's not quite like that. It's just that the process is getting reversed in some way. Okay, so what I said, so let me go back, I think, after this sort of digression. So what I wrote was that, this is what I wrote. Okay, so this Rindler Hamiltonian, which is the right half boost, and then this phi tilde L. So note that this guy is living on the right Rindler wedge. And the reason is, so this also is something you should kind of think about a little bit. As I said, there are various small places which are all kind of somewhat subtle here. So one is this statement. So this is a statement that I wrote down in CPT for Hilbert space of Minkowski space. So the field theory living on Minkowski space, this is how CPT invariance is implemented. Okay? But using that fact, I can make a statement about the Hilbert spaces on these half lines. So what I'm doing is that if I flip my T and X, there is a, you can it's natural to understand that, a Hilbert space living here, there is a natural map from the Hilbert space here to the Hilbert space here. Right? Because I'm flipping T and X, roughly speaking. So, and that map is what I'm using here. So, this defines that operation completely because if I define my action of an operator on all the fields in the theory, it's defined on the full Hilbert space. Okay? So, because of which I can define this guy, but it's also natural. That's what I'm trying to say. Which is that essentially what is happening is that you had a Hilbert space on one half, which is very naturally related to the CPT conjugate Hilbert space that is living on this side. Okay? So, yeah, that's what I defined this phi tilde L to be. Okay, so now let's compute this object. Okay, so we had this guy, and what we want to do is we want to compute this. So the point is that we want to write down this final expression, this vacuum state in Minkowski space, in terms of the two Hilbert, Hilbert spaces that we have in the left and right, this thing. So that's what we want to do. So let's do it. So this, I will write it like this. Okay, so all I'm doing is basically just inserting a complete set. Okay, so I'll say what this means in a second. So any Hilbert space you can I can expand it in the complete set, which is basically the eigenbasis of that set. Okay, so for instance, if you're talking about Minkowski space, the mode functions of Minkowski space form a complete set for the free scalar field theory there. Okay, but it doesn't have to be a free set of modes. So this discussion that I'm talking about here, note that it is actually completely general. I have not used the fact that the theory is free anywhere. It only uses symmetries and going back and forth between path integral representation of expectation values and the Hilbert space interpretations of them. So that's all I'm doing. I'm not really using the fact, I'm not claiming or demanding that my field theory is free. So even at this step, here you might think that basically all I'm doing is I'm just writing this, e to the minus pi h Rindler. Note that h Rindler is a Hamiltonian acting on the Hilbert space, which is the right Hilbert space. So there I can expand it in the basis. This is the the energy eigenbasis of HR. Okay? So for a free theory, this basis, we can do it explicitly and we can write it in terms of solving wave equations, free wave equations on Rindler, and we will actually do it. Okay? So, but the point I want to emphasize is that this eigenbasis always exists. As long as you have a Hamiltonian, there will always exist an eigenbasis, and I don't particularly care that this basis is free. Okay? So that's why I'm keeping it abstract, but we'll make it more concrete when we actually work with the free theory. Is that point clear?
So even with interaction, omega will start from 0.
It will be bounded from below. There is no statement about whether it is, so I mean I can adjust my Hamiltonian so that it starts from below by moving my, by using shifts and so on. So it doesn't really, it's all that matters here is that it is bounded. It doesn't have to start from 0. Yeah, but here I don't have that much choice, right? I'm working with a Hamiltonian that was in Minkowski space, and then once I choose that, then there is no extra freedom that I really have here. I mean, I can do some things, but they're not major differences anyway, okay? So basically what I'm saying is that, the ground state of the translation Hamiltonian in Minkowski space is what I have fixed. And once I fix that, then I have to kind of act consistently elsewhere. So, so that's, I don't, basically, let me not be too precise here because I don't want to make a statement that is probably wrong. So the thing that I'm saying is that this guy is bounded below. So that's all I want. And that comes from the fact that, Hamiltonian is positive definite. That's all I need. And the Hamiltonian is boost, but it is still positive definite because its time translations are well defined on the right side. Okay? So this is some eigenbasis, and eigenbasis depending on the theory that I have. The thing I was emphasizing is only that this is not necessarily that of a free theory. Okay? So how am I doing on time today? At least I have to finish this. Yeah. Okay. So this is my I'm just inserting a complete set here. That's it. All right. So now I can do this. So now I look at. So I'm using Harlow's lectures here. You can go take a look. Okay. So. So here, and this is where I'm crucially using the fact that CPT is an anti-unitary, anti-linear operator. So I write it like this. Okay. So I'm emphasizing where all these states are living. So CPT acting on phi L is living on phi R, on the right Hilbert space. Okay, that's where the subscript is here. Okay, phi L is a state in the left Rindler wedge, but if CPT acts on it, now I'm in right Hilbert space. Okay, so that's why I'm putting this thing here. And so a crucial property of this is again something that you can find in Weinberg, is that so if you have an operator psi, so the definition of Hermitian conjugation for an antilinear operator is basically that you have phi O psi. Okay, so phi O, yeah. So typically what we have is this thing remains, the gets are not getting interchanged. And the reason for this is that you need to do a Hermitian, a complex conjugation at the end in order to, because of the fact that O is antilinear. Okay, so that's it. So if you want a Hermitian conjugation to respect antilinearity, then you need to make sure that you're doing a complex conjugation at the end. Is that intuitive? So essentially what is happening is that otherwise this guy, if I do a linear transformation here, the thing will remain linear on one side and antilinear on the other side. Okay? So I mean I think it's Weinberg makes that statement, but you can go take a look. So No. Now I'm working in Lorentzian signature, right? Because all of this is Hilbert spaces. So Hilbert spaces are meaningful really only in some sort of Lorentzian language. So there is real-time evolution. So yeah, so this basically comes from the fact that, I had this object, this expectation value, I got by doing a Euclidean evolution here, right? I had a thing here and I did this Euclidean evolution here to get it. So, but once I get this expectation value, now I'm breaking it up into a Hilbert space language. So this e to the minus pi omega y, I will stay there, but the states are all at some particular t equal to 0 or to some time slice. Okay? So yes, you're right that this minus pi, this is not a real-time evolution. It is just a weight, if you like. And you will see that this is basically related to an entanglement weight between two Hilbert spaces. Eventually it will turn out to be that. It's not a real-time evolution. It's just a weight that comes from the fact that the object that we are looking at had a Euclidean origin. Okay, so that this is minus, and it is minus as it should be. Okay, so this thing here is now what I define to be I star L. So the point here is that, see, and this is again a slightly tricky fact. What I'm really doing here is that once I bring this guy over here, so here I'm thinking of it as, using this and the definition of anti-unitary operator, if you like. But then the CPT dagger I'm acting on IR. And if I do that, that object is what I'm defining to be I star L. Okay? So imagine CPT is acting on, CPT will take the left Hilbert space to the right Hilbert space and vice versa. Similarly, CPT dagger will also do that. So because of which, my action of CPT dagger on IR is what I'm calling I star L. Okay, it's just a definition. There is a one-to-one map between eigenbases, the labeled by I on one side, and there is a map that I can define by acting with CPT on the eigenbasis, and I'll get some state on the other Hilbert space. It won't necessarily be the same. Yeah, you can think about it. So let me get to the end of it, and if I still have energy, I'll try to, convince you that that is the case. But it doesn't necessarily have to be the case. And part of the, essentially because this thing evolves backward in time, right? So this I star, so the point is CPT is always flipping the state in some sense, right? So the natural time evolution on this side is boost in this direction. So that's why there is that complex conjugation is what this star is really trying to catch in some ways. Okay, but it doesn't matter for our purposes, as I star is just a label. So let me write it. Okay, so now I have defined all the objects there, so I can just write this thing. I'm just writing this expectation value as okay, so I'm writing this as, again, the sum is over the right Hilbert space, and there is e to the minus pi omega I phi L I star L phi R IR. Okay, if I have not screwed up any signs, this is what you should have. So phi R IR is this, e to the minus pi omega I is this, and I'm rewriting this entire thing as acting on the left Hilbert space. Fine? So now I can just compare with this. So this is, I started with this on the left, phi L, phi R, this is what I started with, and I did some manipulations and got here. So now I can strike off this phi L and phi R here, right? So that means my Minkowski vacuum can be written in this way. Okay, so note that this I sum over HR basically means this should not be thought of as a sum really on HR. It just means that it is on the eigenstates of that HR. Okay, so this ket is, now note that this ket is living on HL. This ket is living on HR. Okay, so I have written the Minkowski vacuum as an entangled states, and this is sort of, you can think of it as an entangled state. This entangled basically means there is a tensor product, but then there are weights for each of those tensor factors, tensor pieces. So I have written this Minkowski vacuum as an entangled state between the left and right Rindler Hilbert spaces, and the weight for that is e to the minus pi omega I, and that pi basically comes from the fact that we started with and we did a half rotation. Okay? So this is sort of this is a structure which is extremely general. You will see it various places, and from here, so now we have the vacuum state of Minkowski space, and now I can trace over the left Hilbert space and compute the reduced density matrix. Okay, so we started the reduced density matrix and showed that it was e to the minus beta h Rindler or whatever. So now what I can do is I can write it if I do this. So let me tracing over the left Hilbert space. Tracing over HL implies I get a new Hilbert density matrix, which is trace over L and of this omega. Okay, so I take the pure state omega, make it into a density matrix, and trace over the left half. So, and it's a small exercise, and essentially you will lose this guy, and you will pick up an extra factor. So, and you will find that. So let me actually put a normalization here. Okay, so this normalization is, you can, so this is basically coming from the fact that I have not been careful about normalizations anywhere here. Because all these path integrals are roughly speaking unnormalized path integrals. Okay, but that doesn't matter so much because anyway when we compute expectation values, we will divide it by 0, get 0, 0 in quantum field theory, right? So I'm putting some normalization here. So, and the answer is this. 1 by z, this, and this is by definition e to the minus 2 pi h Rindler in the eigenbasis, because these are precisely the eigenvalues of that Hamiltonian in its eigenbasis. So that's why it's naturally diagonal. Okay, so this, if I do this, and this is what I got before by just doing in many ways. I got this in many ways in the last lecture, right? So what we have done here is that we got the Minkowski vacuum as a tensor product, not a tensor product, and as an entangled state in the tensor product between left Rindler and right Rindler, and then we took a trace on the left half and we found this answer. So the point of this was easier to find for many reasons. One is you could just get it from the Euclidean argument because you're doing a full 2 pi. Here on the other hand, because there is a cut in the path integral, you have an actual Lorentzian state. So that state is the Minkowski vacuum. Okay, and that Minkowski vacuum we wrote it in terms of this, and now we have explicitly shown that the temperature. And this also tells you that the temperature is 1 by 2 pi, temperature beta or whatever. Okay, so that's the sort of main punchline, and this calculation. I mean, it has various small pieces which are kind of I think it is a good idea for you to go through it in some detail. Okay. So because it is, there are various things, I have tried to emphasize them, but I don't think in one iteration you might not have registered all of them. But it's a good thing to kind of go back and look at various things. But what is the point of this? The point of this is that this structure here, this is called a thermofield double. Okay? So the thermofield double basically says that it's essentially a purification. A purification is you start with the density matrix. This density matrix is, it's not the density matrix of a pure state. It's a thermal density matrix, but it can never be pure. So, but the thing is, this state on the other hand is a pure state. But the price that you had to pay in order to get the pure state is that you had to double your Hilbert space. So you had here this object is defined on the right Hilbert space. Okay? So, but when you purify it, but the claim is that, or the observation here is that by doubling the Hilbert space HR with another copy of itself essentially, which is HL, you can construct a new state, which is this. And this state, when you trace over the left half, you will basically get the thermal density matrix. And it's more generally true. So an interesting fact about these kinds of thermophile double constructions is that if you were to compute an expectation value of an operator on the right Hilbert space, you can compute it by, so if you just compute the expectation value, okay, so you put, let me just write it. So let's say you wanted to compute O right omega. So then that's the same thing as trace rho r O. Okay? So this omega here is basically a Hilbert space that is the full Hilbert space of Minkowski space, if you like. But you can do that if this operator is on the right wedge. Okay, if it is an operator living on the right wedge, then you can compute it this way. So this construction is, so yeah, whenever there is a thermal density matrix, you can purify it using this sort of a construction. So let me write the general thermophile double. Let's say that you have a thermal density matrix which is rho T is e to the minus beta H. Okay, now I'm moving away from Rindler and Minkowski and all that. I'm just making a general statement. Okay, so if you have a general density matrix of this type, what I can do is I can purify it. Or more precisely, what is called the thermophile double state associated to this thermal density matrix is okay. So this was some Hilbert space, which let me call it H right, in analogy with Rindler. So this has nothing to do. Now I'm changing gears completely. Okay. So and this will be valid for any system, any thermal system. So I'm looking at thermal density matrices in general. Okay. And the claim is that this thermal density matrix is basically some trace in some Hilbert space, and that Hilbert space is HR. Just calling it HR by analogy with Rindler, but it has nothing to do with Rindler. So, and then the claim is that this is some object that I can define like this for, whatever the beta might be, I can construct a state of this form, e to the minus beta ei by 2, and so note that I have doubled the Hilbert space. So it's a tensor product of two Hilbert spaces now, and I'm looking at a specific entangled state in that doubled Hilbert space. Okay, so this state is not a tensor product state. It's an entangled state. In this basis, then the eigenbasis that I'm working with, this is an entangled state, and it's entangled in a specific way. And this state is what is called the thermophile double state, and this is, sort of a natural generalization of what we saw here.
So using I instead of I star.
Yeah, I should put an I star. Yeah. Any questions? Any questions from, I think this is kind of like, a conceptually important lecture, and there will be a few more, so I'll try to kind of stagger them. So the next lecture will be kind of like, next lecture is somewhat also important, but after that we will have like, slightly easier time, and then maybe we'll come back to something a little bit this thing. So yeah.
Is it like that the temperature is coming with the entanglement of the vacuum with the
the point is that the Rindler, so the temperature is clearly there. So I'm okay. So I guess the surprising bit here, if you like, is the fact that when you traced out, so it is not surprising that you started the Minkowski vacuum and you traced out part of it, okay, that you got a density matrix, because that's what density matrices are. They are reduced density matrices, so you'll always get something. What is surprising here or interesting here is the fact that the Rindler thermal density matrix that we got can be obtained in that way, starting from the Minkowski vacuum. So the interpretation, usually the interpretation that is given to it, and we will see, we will do it in slightly, different approach maybe in the next lecture, and that's also important. So there are multiple ways of looking at it. So, and once we have that, you will kind of see that the way to think about it, maybe at least heuristically, is that an accelerated observer sees, accelerated observer is basically still living in Minkowski vacuum. right? He is not really like, there is no, the state hasn't changed, the background space-time hasn't changed. So if you're accelerating, somehow the idea is that you are seeing Minkowski vacuum as a thermal bath. So that's one way to think about it. Okay, so, but it's, yeah, so, right, I mean the connection between Lorentzian and Euclidean field theories and, temperature is probably some of the deepest questions, so I don't really have much more to say.
But my question was that in the quantum field theory, we know that at space-like separations, we have a finite transition probability amplitude, like the correlation function is finite. So,
Where, sorry, I didn't get it. So
the correlation function that we calculate in UFT, that is finite at the space-like separations, right? That is finite at the space-like separations. So because of that,
finite or it's the commutator has to vanish.
Yeah.
That's what it's true. It is the correlation function itself. Like if you compute, like if it is some phi x phi y, it doesn't have to die, right?
Yeah, it doesn't have to die.
Yeah.
That gives rise to some entanglement structure in the vacuum. So my question.
Yeah, it could be. Yeah, but the entanglement, it does give rise to an entanglement structure. So this is kind of exposing the entanglement structure between the right and left halves of Minkowski space. So if you like, so this is, so it's certainly related, and this is one way to kind of show that Minkowski space is highly entangled. Okay, so I also want to say one more thing, which is that this is somewhat heuristic expression. Okay, so as I said, this, in general theories, for instance, in interacting theory, this I, for instance, is, generally speaking, we don't know how to write it. Right? In interacting theory, but it is still true that whatever might be the theory, its spectrum has to exist as long as it is a Hermitian operator and it has bounded from below, etc. Its spectrum is well defined. So this guy has to exist. So, but we will do this explicitly for free theories, maybe next lecture or one of these lectures, depending on my energy level. It requires some writing. Okay, so I think, question? Yes.
So in ADS, what we was in that.
In where? ADS. Okay.
So like
if there is an entanglement between the left and right axis, it somehow builds a wormhole.
Yeah. So this is sort of a collapsed wormhole, right? So you have one wedge here and one wedge here. So this is in some sense sort of a trivial wormhole. So here, for instance, the difference, as I said before, is that in the case of black holes, the point at the center here is actually a sphere because the extra S2 has not shrunk to zero size. Here, on the other hand, it has shrunk to zero size. That's the nature of Minkowski space. So in some sense, there is a collapsed wormhole sitting there, if you like. I mean, here, it's a sort of a trivial wormhole. You just have to stop accelerating, and if you go like this, you will get to the other side, right? So wormhole basically just means that there is a way in which you can reach the other region. That's really all that it means. And in the case of black holes, maybe it is a bit more picturesque because there is an actual sphere. You have to go through the sphere to get to the other side. Here, on the other hand, there is no such thing because that sphere is basically collapsed here. So it's not very interesting in that sense. But it's still, you can. It is in some sense, it's a wormhole, if you like. It's kind of a trivial wormhole, but it's a wormhole. Any other question?
So here we have rotated from the left hand side to right hand side.
Right.
We have a CPT from the left to right because we take a Lorentz boost in the right hand side. Right? So if someone had to do this thing in the left hand side also, so we had to do a CPT on the right.
I mean, it's basically a definition of how you are defining your rotations and so on. So, you have to pick some choice, right? So if you're defining some group action on the space-time, then you have to say, okay, t going to minus t and x going to minus x. So that choice, if you change it, there are some of the other things, things will accordingly change. So it's not really like a very big difference. So in a way of, like you could always ask this question of why am I not drawing my t this way and x this way, but why don't I draw my t here and my x here? Why don't I draw my real line starting from minus infinity here and ending with plus infinity here? I could do that. It'll just change some conventions, but it's fundamentally the same thing, right? So it is not like So if you want to go from this kind of a coordinate to this kind of coordinate, there will be some sign changes, and if you're like implementing it in some Hilbert space, etc., you'll have to do various things. But it's really like the same sort of thing. It's not very different. Any other questions? Okay, if not, then let's stop here.